The question is, what is a radian? Okay, looking at some of these answers we have here. You tell me. What do you think? Correct or incorrect? Measure of an angle, is that correct? Absolutely. Okay, so if you said that, that was good. That has the same linear measure as the radius of the circle the angle is in. Now when you say the measure of the angle has the same linear measure, you've got to be careful here. There's a little bit missing on that piece. It is the measure of an angle, and we are talking about the radius of the circle, but let's go on. The length of the radius wrapped around the circumference, that person needs to do a little more review, and when you see the videos on YouTube, you can go back and review. The measure of an angle that opens an arc, okay, so now we're talking about the arc, and we're assuming that they mean the arc has the same linear measure as the radius of the circle. That, I would say, is very complete. Okay, we talk about it being the measure of an angle, that it's the arc that has the same linear measure as the radius. Okay, so that one's very good. An angle whose arc has the same linear measure as the radius of the angle, very good. A measure of an angle that opens an arc that has the same linear measure, very good. Okay, are we able to see now what needs to be? Okay, so for the most part I say bravo, you guys have it. You know, if you don't have a complete sentence on, you know what it takes to be complete. Measure an angle, opens an arc that has the same linear measure. You're repeating exactly what it is. Hopefully you're not just repeating, you're understanding. And that's what we need to be sure we understand. We have. Okay, I'm going to save these to the portfolio for part of what we're going to be doing today. And let me give you another question here. Another question. What is the input variable of all trig functions? Okay. Forgetting to record now. I'll just go back and repeat that we've got some very good answers here, and that when we're talking about this answer, these are the names of the functions. I'm just doing this for the sake of the recording now. These are the names of the functions. They tell us what two sides to use in our computation of the ratio. Okay, let's then put that aside, and we'll go to our notes here. Okay, we're going to hopefully take care of section 2.4 today, or at least most of it. Next week, we're going to look at section, whatever's left of 2.4, get into section 2.5, and I'm really anxious to talk to you about section 3.1. So I think we're going to be able to next week. If not next week, we'll get into it the week after that, into section 3.1. It is the, kind of like the kingpin, the major idea behind the rest of the semester, or at least the majority of the rest of the semester. So let's take a look at section 2.4. We've been talking about limits. We've talked about one-sided limits already, in the fact that if a limit exists, it means that we are able to approach from the less than C value and from the greater than side of the C, of that value C, and that our outputs are behaving the same. Our outputs are going to the same value. So we've already talked about one-sided limits. We're going to look at some problems that specifically you have to look at one-sided limits because it's not an obvious thing otherwise. But before that, we're going to talk about this thing of a continuity. Now, if I were to show you a graph and I just say, is it continuous, you probably have a intuitive thought about continuity. Or maybe you've studied it before and you have a way that someone has told you how to determine if a graph is continuous. Anyone want to share what that is? Okay, then let me give you what I'm thinking of here. If I do something like this, and we'll call this, well, we know that's at 0. We'll call this at A, and we'll call this at B here. Can you tell me, is that graph continuous everywhere? No. Why not? What is it that you're looking at that tells you that it's not continuous? Lindsay, you gave me a response back there. Okay, so at B there's an asymptote, we would know. Kind of an asymptote because I do have that point there. Okay. So at that point, that's the only point that's not continuous? Okay. Molly, jump in and help us with the next one.
There's a hole.
Okay. And so because that hole is there, we can't, it's not continuous. Okay. What else? There is one other. I'll give you a hint. Yeah, Emma. Okay. Now, there is what's called the pencil definition of continuity. Have you ever heard of that? If you had this on your paper and I said start at the left side and trace this all the way to the right side, you know, start over here on the input value of this one and trace all the way on the function, could you trace it without lifting your pen? That's called the pencil definition. Okay? If you cannot trace it without lifting the pen and putting it back on the other side, you can't see me lifting the pen, but I am, and putting it back on the other side, then you know that it's discontinuous at that point. Okay? So that's kind of the intuitive idea. Now, we can use that intuitive idea, and it will carry us quite a ways if we see the graph. If we see the graph. If we don't see the graph, we've got another issue. So here we have now our analytical definition of continuity. We have that and remember I read these as the output, so the output of the function at the input C, the output is defined. Okay? If the function is continuous, the output is defined. So if we look at f of 0, the output is not defined, therefore we know it's not continuous. Okay, so if we look at this and say at f of 0 is not defined, therefore f of x is not continuous at x equals 0. Okay, that would be one statement we could make about that. The next one says the limit exists. Okay, so we have these three criteria, these three conditions, all three have to be met. The function has to have a value, an output value at the point. If it doesn't, it's not continuous. We're done. If the function is defined at a point, but the limit does not exist, then it's not continuous. So let's move over to this point here. Is the function defined at A? Yeah, I've got a dot there, right here. Okay, so the function is defined at A. Is the limit, does the limit exist? And so I'm going to change pens just so we can kind of keep things a little straight. So we'll move this down here. We could say that f of A is defined. Okay, check mark, that one's done. But now the limit as x approaches A Does not exist. And now the reason would be two different one-sided. Yeah, two different one-sided limits. Okay, so at A, so we say therefore f of x is not continuous at x equals A. Okay? The first criteria worked. It was done. Second criteria did not. Okay, actually, you know, I'm going to go back and change this, because this is not the way I want to draw this for this next one. So let me just rearrange this a little bit. There we go. And we'll call that at B. Okay. Oh, let's see. We haven't used, we'll use red for this one then. Okay, so here we go. Is f of B defined? Yeah, there's a point right there. It is defined. So f of B is defined. Check mark. Is the limit as x approaches B, does that limit exist? Yeah. As I come up to here, whatever that value is, and come down to here, it is. So we would say that it does exist. I'll just put the word exists there. Okay, check mark. Now the third criteria comes into play. Let's go back. I guess maybe I do need to put a few values on here. So let's say this is, let's call this N, and we'll call this down here P. Okay? So f of B is defined, and we can say that f of B is equal to P. And we can say, I'll erase this now and put down that the limit has a value. We know the value now is N, whatever that N and P stand for. Now we come to the third criteria. Is the limit as x approaches B, does the limit value equal the output value? Well, we have, this is, let's see, this is N and this is P, and those do not equal. Okay, not the same thing. So therefore, f of x is not continuous at x equaling B. Okay, three criteria. All three have to be met in order for continuity, analytically, to discuss continuity. Again, pencil-wise, the pencil definition, we could see that in fact it is not continuous, but we need the other. Okay, now I'm going to save the recording here and make sure. Oh, what to say at the bottom? Okay, before I save it, let's go back and look at that. Yeah, sorry, my pen was stubbing here. F of x is not continuous at x equals B.
Was that a P?
That's a P.
What about it?
Here?
No.
That's a B. Sorry about that. Yeah. Okay. Yeah, anything else you can't read? My handwriting deteriorates, and then as I move with this, sometimes I drag my hand across this pad, and that's what makes it not right as well. Okay, anything else? Okay, let's